So, welcome to Chapter 9, Analysis of Algorithms. I'm Noson Yanofsky. The chapter is called Medians and Order Statistics. It's about, if you have a list, how do you find the best, how do you find the worst, how do you find the median, how do you find the max, min, etc., etc. Okay, so this is one of my favorite chapters because the questions you describe and the algorithms you can present them to sixth graders and they'll think of algorithms, and the algorithms that the book comes up with are totally different, better, and very good. Okay, so beforehand I gave you a homework. It's called Homework Questions Before Chapter 9. I wanted you to think of ways of doing things and then to see the way that they do things. So I'm sure you all did it. Let's go through it. Write an algorithm to find the maximum element in an unsorted array. So here we have a bunch of cards. This is an unsorted array. Okay, and we want to find the maximum. Okay, so the maximum, the only way I know how to do this is consider him to be the max so far. Compare it to him. That's 1 comparison, 2 comparison, 3 comparison, 4 comparison. He's bigger. 5 comparison, 6 comparison, 7. He's the max so far at the end, and so we're absolutely done. So how many comparisons do you have to do? And the answer is you don't compare anybody to this. You assume he's the max so far, and then you go through the rest of the list. And so in this case, the max, so you can do it in, you have 8 cards, you could do it in 7 comparisons, but if you have n cards, you could find it in n-1 comparisons. So that's probably the best way to do things. Okay, how many comparisons are done by the way, what's the best case scenario? Here's the best case. Well, what is the best case scenario? It's still, you still have to go through the entire list, and so it's still n-1. Okay, how about how many comparisons are done on average? You still have to go through the list all the time. How many comparisons are done in the worst case? Okay, do the same for the minimum. Okay, so the max in all 3 cases is n-1. Do the same for the minimum. Okay, well, same thing. You assume he's the minimum so far, then you do 1 comparison, these two, okay, and you find he's the min so far, then you do another comparison, you find he's the min so far, then you go through these, all the rest, and you find he's the min so far. Okay, same thing here. For the min is n-1 comparisons. Very nice. Okay, and that's the same for average, worst, best case scenario. You have to basically go through all n cards, assuming the first one is the one you want. Okay, so that's problem 1 and 2. Good. Obviously problem 1 and 2 is pretty simple. I don't know any better way of doing problem 1 and 2, so that's pretty simple. In other words, if you're going to find the maximum, the extreme of any set of cards, you have to look through every single one of them. You're not going to get through better than n-1. Great, let's do number 3. Write an algorithm to find the maximum and the minimum of an array. Okay, so the maximum and the minimum. Okay. We're going to do this a few different ways. Okay, and it's a shame that, okay, we're going to do this a few different ways. So here we're doing the max and the min. Okay, and one way I guess we'll call the baby way is very simple. Okay, namely, go through the array, find the max, and go through the array again and find the max. So how many comparisons, and find the min. So you have to go through the array two times and you can find the min, so the max and the min. So that's n-1 comparisons to find the max plus n-1 comparisons to find the min. Okay, and that's 2n-2. Okay. Question: can we do any better? Okay, can we do any better? Okay. And the answer is yes, you can do better. And here's where it gets a little bit more interesting. What you can do is you can assume, what are we doing here? We're finding out if the maximum and the minimum of the array. And what you can do here is as follows. You can look at these first 2 cards. Okay. You look at the first two cards and compare them. So this is larger than this. Okay, great. Now, what you want is to compare this guy to it. Now, all you have to do is, let's compare him. I'm sorry, I usually do this with people, looking for the oldest and the youngest person in the room. So this is a little bit strange for me to do it with cards, but we'll do it. Okay, now, he's older than him. Fine. Now you do this. Now here's one thing you could do. Try him, see if he's older than the max. Okay? Okay, he is not older than the max, so he could be he could be younger than the min. So you have to try and see if he's younger than the min. He is. Okay, fine. That wasn't very helpful. But now let's do this. Try the next one. Okay, so by the way, he is, let's do this. He is now max so far. He is now min so far. Great. Now try the next one. Okay, compare him to max so far. Okay, 29 is bigger than 23, so what do? We automatically make him to be the max so far. He's still the min so far. But we only did one comparison. Now, if he is larger, since he is larger than the max so far, I know one thing for sure. He's not going to be smaller than the min. So there's no reason to compare 29 to 18. Okay? Now let's do the next one. 20, compare 20 to 29. Okay? He is not as large as this, so he fails this comparison. Well, then you have to compare him to there. Okay, so you're going to have to compare him to the second key. Okay, to the min so far. Great. He fails that too. He is not, 20 is not less than that. And you go on like this. 24. 24 is not larger than the max so far. Okay, and it's not larger than the minimum. The point is, for all the cards, you're going to have to do either one comparison or two comparisons. Let's do another example of this. Okay, let's do another example, because that was a little bit messed up. Okay, you have 23 and 20. Very good. Okay, now what you're going to do is you're going to compare these two. You're going to make him, he is larger, he is smaller, so you're going to make him the larger, he's the smaller. Great. Now you're going to compare 21 to the larger. That fails. Then you see, so that's one comparison. Then you see, how does he compare to the smaller? Okay, he fails. 21 is in between 23 and 20, so we don't do that. Next, 19. You're going to compare 19 to, is he larger than the max so far? No, he's not. Then you're going to compare it, is he smaller than min so far? Yes, he is. Great. Next, so you had to do two comparisons for them. 24. Is 24 larger than 23? Yes, he is. Conclusion, you did one comparison, you find him larger. There's no reason to compare him to the smaller one. Great. Now let's do the next one. 29. Is 29 larger than 24? Yes. So you make him to be the larger so far. Notice you only did one comparison. So sometimes you do two comparisons, sometimes you do one. Now let's do 22. Is 22 larger than 29? No, it's not. Okay. So now you have to do, is 22 smaller than 19? No, it's not, but you did two comparisons. Okay. And now you do 18. Is 18 larger than 29? No, it's not. Is 18 smaller than 19? Yes, it is. You did two comparisons. So with this method, you can do, sometimes you do two comparisons, sometimes you do one comparison. Okay, so let's write it up. Okay, so this we'll call the intermediate way. Okay, and let's see how many comparisons do you do. Well, in the worst case, you're going to do two comparisons every single time. Okay? In the worst case, you're going to do two comparisons every single time. Now, when does the worst case happen? Very simple. When your first card that you choose is the total maximum, then watch what happens. He's the max, he's the min, he's the max so far, he's the min so far. He's the max so far, he's the min so far. That's very good. But now, every single time, you're going to compare it to the max so far, going to compare it to the max so far, going to compare it to the max so far, going to compare it to the max. And each time you're going to have to do, it's going to fail, because that is the max. Okay? And you're going to have to go through every single one. So in the worst case scenario, you're going to have to do 2, I'm going to be a little sloppy here, 2 times n comparisons. It's not really n because these first 2 cards you're only doing 1, but let's be a little bit sloppy here. This is 2n comparisons. For every card you have to do 2 comparisons. Okay? The best case scenario, okay, what's the best case scenario? The best case scenario is probably this. Well, let's just start. Okay, you do one comparison here. Great. Now you compare. This is the max. So this is the max. So you're gonna have 20 to compare it to 19. Okay, 20 to comparing to 19 is bigger. No, right. 20 comparing to 19 is 20 is bigger. So you're gonna make this the max. But you only did one comparison. 21 compared to 20. Okay, that's bigger than that, so you only do one comparison. You make him the max so far. Great. Next, 22 compares to 21. You do one comparison, you make him to be the max so far, but you never start up with that 18 again, because you're always going in increasing order. Same thing here. You're going to compare 23 to 22. You're going to compare 24 to 23, you're going to compare 29. So when it's in this ascending order, that's when you get the best case, and basically that's n. You basically do one comparison for each one, because you're never going to compare it with the second, with the min so far. Great. Okay, how about the average case? Okay, and the answer is, what happens on a typical case when your thing's all messed up? Well, sometimes you're going to do 2 comparisons. Sometimes you're going to do 1 comparison. Okay, it doesn't. The example we saw was like that. So you may as well write that as 1.5n. Again, we're not being exact. Okay. Now, all these things we did we did it one way. What was the one way we did it? We took every new card and compared it to max so far, and then if we had to, if it failed the comparison, we also compared it to min so far. Okay? We could have done it the other way around. We could have taken every new card and compared it to min so far. Let's do a typical example. Okay, here's 2 cards. He's larger than him, so he's max, he's min. Okay, and then what do? We take 22, compare it to min so far. He's more than min so far. Okay, so he's not going to be the new min so far. And then we compare it to max so far. Oh, now he's the new max. Great. Now let's do this. 18 compared to 19. He's the min so far. 18 compared to 19. 18 is smaller, so he becomes the new min so far. We only had to do one comparison. 20 compared to 18. No, he's not smaller. Okay, so we have to compare it to that. No, he's not bigger than that. 20 compared to 18, smaller, etc., etc. I'm sorry, larger, so we don't have to do that. But okay, so again, the first time I showed it to you, we took every card and compared it to the max so far. Well, we can also compare it to the min so far and do that. Okay, but that's the way we do this. Question. Okay, so that's the intermediate way. How many comparisons are done in the worst case? 1.5n. Good. Good. Okay. I'm sorry. How many comparisons are done in the worst case? 2n. I'm sorry. How many comparisons are done in the worst case? 2n. Can we do better? This is question 3c. Can you do better than 2n in the worst case? And the answer is yes, but it's a very clever way. So, book's way, I'll say it in the book's way. I think it's a homework question in the book. Okay? And this way is worst case 1.5n. So we like that. If something in the worst case is 1.5n, then we like it. However, I just have to say, it's also in the average case and in the best case also 1.5n, but it's a very clever way of doing it, and I'd like to show it to you. Okay? The way to do it is as follows. Let's make green, sorry. Hold on, just don't move. Let's make green to be min so far, and max, and red to be max so far. Okay, so here's a clever way of doing it. You ready? Take the first two cards. Compare them. 21 is larger than 19. Very good. 21 is larger than 19, so we're going to make 21 to be max so far, and then 19 to be min so far. Great. Now I'm going to take the next two cards. I'm not going to do it one card at a time. I'm going to take the next two cards, 22 and 18. Now let's see. What do I do here? What's larger, 22 or 18? Answer 22. So I just did one comparison. I found which one is larger here. Now I'm going to compare the larger here to the larger there, and I'm going to compare the smaller here to the smaller there. Okay? Question, what's larger, 22 or 21? Answer 22. So I'm going to make him the new max so far. What's smaller, 18 or 19? 18 is smaller. I'm going to make him the new min so far. Great. Now I'm going to take the next two cards. I'm going to do one comparison. What's larger, 20 or 23? Answer 23. And so I'm going to compare 23 to the max so far, 23 to 19. What's larger? 23, so he becomes the new max so far. What's smaller, 18 or 20? Answer, 18 is smaller, so we leave that alone. Great. Next, I'm going to take the next two cards. 24 and 29, what's larger? That's one comparison. 29 is larger. I'm going to compare 29 with the max so far. 29 wins, so 29 becomes the new max so far. And what's smaller? 24 or 18, 18 is smaller, so we have it like that. Okay, so question, how many comparisons did we just do? Okay, you have to understand, forget about the first card, because I'm going to be a little bit sloppy here. Forget about the first two cards. Okay, imagine you have n cards. For each of the n cards, there were n over 2 pairs of cards. Let's go through that again. There were n over 2 pairs of cards. Okay, I was doing them two at a time, so there are n over 2 pairs of cards. And what did I do for each one of the pairs of cards? I did one comparison between them to find out who's the max. Okay, should I do it this way or this way? And then I took the max and compared it to the max of these two cards, compared it to the max so far, and I took the min and compared it to the min so far. So for this pair of cards, I did one comparison to do both of them, then compared one of them to the max so far, one of them to the min so far. So altogether for each one of the n over 2 cards, I do 3 times n over 2 comparisons. 3 comparisons for each of the pairs. Okay? And that's equal to 1.5 n. That's very nice. Okay? That's a clever way to do that. Okay, so that's 1.5 n. In the worst case scenario, it's also in the best case scenario because it doesn't matter about the data. You're going to try every single pair, and in each pair you're going to do 3 comparisons. So we're done. Great. Let's do question number 4. Write an algorithm that finds the maximum and the second maximum. Okay? The maximum and the second maximum. Okay, so let's do this. We're going to again do this 3 different ways. Okay, the baby way and the second and the intermediate way and second max. Okay, so let's do it. What's a baby way of doing it? Very simple. Go through the list, find the maximum. Here's the maximum. Go through the list to find the second maximum. In other words, if you want, you can take the maximum, move it to the different way of the array. Now go through this rest of the list and find the second maximum. And there you have it. The second maximum, go through the list, you find that, so you have that. Okay, let's see how many comparisons were done there. Well, to find the maximum, you had to do n minus 1. I'm being exact here. To find the second maximum, you have n minus 1 rest of the cards. Okay, and so you consider the first of those n minus 1 cards. You're just looking at n minus 1 of these cards. You consider this the max so far. You consider the first one max so far, and so you have n minus 2. So this is equal to 2n minus 3. Great. Can we do better? Can we do better? That's a question we always ask. Can we do better? To find the maximum and the second maximum. Okay? And the answer is yes, we can. Okay? We could do something similar to what we just did. No, I'm sorry, something to what we did the intermediate way of the previous example. Okay, let's go through it. Okay, here's what we do. We take these two cards. Yeah, we take these two cards. We take these two cards. Okay, this is larger than this. So here's larger than this. Great. Now we're going to take the next card. Well, there's two ways of doing this. One way is say, okay, question, are you larger than Max? The answer is no, he's not larger than Max. Well, then we have to check if he's larger than second Max. Okay? Okay? And the answer is no, he's not. Fine. Okay? Now we try this card. Question, is he larger than 24? No, he's not. So we have to try. Is he larger than 22? No, he's not. Sorry. Let's do. I think that's a little bit better example. Well, let's do this one. Great. First, take two cards. He's larger than this. Very good. Now we compare him. Is he larger than him? Okay, and the answer is yes, he is. So he becomes Max. Okay, and he becomes second Max. Great. They both moved up. I mean, they both moved. Right. So 24 became Max. 22 became second Max. 19 is now so far third Max, but we're not asking that question. Great. Next, is 18 larger than 24? Okay, answer no. Did one comparison, said no. Is 29 larger than 24? Yes, it is. So he becomes Max, and he becomes second Max. Very nice. Be nice. Okay, great. Now, is 21 larger than 29? No, it's not. Then I have to do, is 21 larger than 24? No, it's not. Okay, I think I'm done now. Okay, next, is 20 larger than 20? Okay, anyways, for the next three of them, I have to do two operations each. Is 20 larger than 29? No, it's not. Is 20 larger than 24? No, it's not. Is 23 larger? No. 24? No. Okay, so sometimes I do one comparison, sometimes I do two comparisons. Okay, so in the best case scenario, I would do n operations. Okay, when will that happen? When will it happen that I'm only going to do one comparison each time? And the answer is that will happen in ascending order. Let's go through it. Ready? 18 and 19, which is the larger? 19. Okay, great. Now I'm going to try 20. Okay, I'm going to try 20. Okay, is 20 larger than than 19? Yes, it is. So he becomes larger. He becomes second larger. Next, I only did one comparison, by the way. Okay, is 21 larger than 20? Yes, it is. So he becomes Max. He becomes second Max. Is 22 larger than 21? Yes, he is. Each one I'm doing only one comparison until I finally get to there. Okay, so that's that. Great. Okay, what about the worst case scenario? The worst case scenario is 2n comparisons. Let's see when that happens. Well, that happens exactly in the descending case. Let's go through this and see why. Okay, I'm going to compare these two. I'm going to say he's larger than him. Very good. Red is hotter, so he's larger. And then we do as follows. Compare 23 to 29. No, he's not bigger. Okay, now compare 23 to 24. Oh, I'm sorry, I don't need this. Well, I'm sorry. I'll give you another case where this is, I don't care. Okay, we can mess this up even more. Okay, you ready? He's the larger. He's the second largest. I don't even need that. Let's do this. Okay, great. I've come to these two cards. I compare them. He's higher than him. Very good. Now, I compare him. Is he larger than 29? No, he's not. So what do I have to do? I have to compare him to 19. He is larger than 19, so he becomes the second largest. Okay? Now, 20 to 29. That's one comparison. He is not as big as 29. 29 is the biggest. As long as the largest element is in the first place, I'm always going to do two comparisons. Now, 20 to 24? No, he's not. 21 to 29. That's one comparison. 21 to 24. Two comparisons. Each one I'm going to do two comparisons. Look at it. Each one I'm going to do two comparisons. So the worst case is 2n. Okay? And on average, sometimes I do one comparisons. Sometimes I do two comparisons. So the average case, 1.5n. Great. Now, let's do the book's way of doing this. Okay? But before we do the books, I have to tell you a story. Okay, I have to tell you a story of an old man who was a friend of mine. And, well, okay, so let me just tell you the story. It's about this old man used to walk around with a newspaper clipping in his pocket. And in the newspaper clipping, it describes him as a teenager, and he had gone to a chess championship. Okay? He had gone to a chess championship, and he had played Boris Kasparov. And Boris Kasparov won him. He beat this guy when he was a teenager. But this was a very prideful thing of him, that he had played Boris Kasparov. He had lost Boris Kasparov. He told me right then, he told me, whenever you told me this, and he told me the story many times, he said Boris was better than him. Boris Kasparov was better. Boris Kasparov was a better chess player. But he said something interesting. But before we tell you what he said, I got to describe to you how a chess championship works. What happens is there's about 128 people who sign up to go to a chess championship. Okay, I'm making up numbers here, but that's for educational purposes. Okay, there's about 128 people. What happens is the 128 people are gathered into a giant hall. In the hall, there are 64 tables. Okay, and what happens is everybody mulls around and walks around. At some point, the guy in charge of the chess championship blows a whistle or rings a bell or something like that, and everybody randomly chooses a table that they sit in. Okay, I'm slightly making this up, but that's okay. Okay, they randomly choose a table that they sit in. They sit down at the table, and then they play. So there are 128 people playing 64 games. Okay, and there are referees walking up and down to make sure that there's no problem. Anyways, at the end, anybody who lost the game, we're not going to talk about draws, anybody who lost the game stands up and walks out of the hall. They're finished. They're never in the game anymore. Okay? They're never in the game anymore. Now, who's left? Okay, well, there are 64 people left in the hallway. Everyone in the hall, every one of the 64 people just mulls around. Meanwhile, they take out 32 tables They had 64 tables. They take out 32 tables. They are left with 32 tables. Okay? And the 64 winners of the previous round, I'm not describing anything different than basketball's, you know, trials, etc., or many sports different do it the same way, but the story was told to me about chess. Okay? Then, there are 32 games played, 64 players, 32 games played. Again, they walk up and down the aisle. Then, the 32 losers walk out of the hallway, and then there are only 32 winners left. Okay? The 32 winners play, they take out half the tables. There are 16 tables. They play 16 games. Okay? The winners of those 16 games stay. The losers walk out of the room. And they play, and then they play 8 games, and then 4 games, okay, and then 2 games, and then that's when they turn on the televisions, let everybody watch. Nobody's really interested in the earlier games, and finally there's one game left, okay, and the two best, I'm sorry, shouldn't have said that. The 2 last players are playing each other, okay, and that's usually broadcast. And there's a giant screen behind them showing what every move is made, etc., etc. Okay, and that's the way you play a chess championship. Okay, so my friend used to say the following statement. Okay, he used to make the following statement. He used to say, look, I played Boris Kasparov. I lost to Boris Kasparov. He was a better player than me. But I was the second best player in that game, in that championship. In other words, from the 128 people there, Boris was number 1 and I was number 2. Okay, now let me tell you why he legitimately had the right to say that. I don't know if it's true, but he legitimately had the right to say that. Because he was a little kid and he went to play in this chess championship. He didn't know what he was doing, and he walked around and he was mulling around, and then he just saw someone sitting at the table at the first game, and he sat down there. And who was sitting across from him? Answer, Boris Kasparov. Okay? And he played Boris Kasparov. He lost to Boris Kasparov. But my friend said that he was the second best player in the entire championship. Okay? Now, I want to explain to you how that works. Okay? He had a point, and I'd like to show you. So, it has to do with what we're talking about, and I'd like to show you a way of finding the maximum and the second maximum, the right way to do it. Okay, so let's just erase this. Okay, and I'll show you the method of doing it. It's called the tournament method. And it goes as follows. This is the way it's done. This is exercise 9.1-1. 6, 2, 4, 7, 18, 17, 5, whoops, 5 and 12. Okay. Now you want to find from these 8 numbers, you want to find the best and the second best. So here's what you do. 6 and 2 can fight it out, 6 is larger. 4 and 7 can fight it out, 7 is larger. 18 and 17 can fight it out, 18 is larger. 5 and 12 can fight it out, 12 is larger. Okay, great. Then you have the winners play each other. 6 and 7 fight it out, 7 is larger. 18 and 12 fight it out, 18 is larger. And finally you have 18 and 7 fight it out, the match championship, and 18 is larger. So this is the way we find the largest element. Now let's just see how many comparisons. Maybe this is a better way of finding the max. Well, let's just see. We have 8 cards, and we did 1 comparison, 2 comparison, 3 comparison, 4, 5, 6, 7. 7 comparisons. It's n minus 1. That doesn't save you much. But now we have the following question. How do you find the second largest? Okay? Who is the second largest? Is 7 the second largest? No, he's not. Okay? Is 7 the second largest? No, he's not. He's a potential second largest, but he's not the largest. Okay? Okay? How about 12? Is 12 the largest? Could be. How about 17? There's the second largest. Okay? And the point is as follows. The point is as follows. What does it mean to be the second largest element? That means if you played anybody else, you would lose. I'm sorry, if you played anybody else, you would win, except for one person, the largest. So what you have to do in order to find the largest is go through the list. Go through this championship thing and compare it. Now here's how you do it. You say, okay, 7, that's one of the largest. 12, 17. Who's the maximum of 7, 12, and 17? Answer 17. And this explains what my friend was saying. He said, yes, I was knocked out the first. But had I not played Boris Kasparov the first time, I would have made it to the 5th round. He said, I would have made it to the last round. And I would have played Boris Kasparov in front of everyone else. I would have lost to Boris Kasparov, but I would have been the second most. So the point he's trying to say is, this guy, the last person to win the winner, is not necessarily the second best. Okay? You have to go through the rest of the chart in order to find it. Okay, so this is called the tournament method. Question, how much work is done for the entire thing? And the answer is n minus 1 for that, to find the maximum. And then how many levels are there to find you have to go through all of the rest, and the answer is as follows. Plus log of n, that's how many levels there are, or how many games that he won. He won one game, he played one game, 2 games. I'm sorry, he played 1 game, 2 games, 3 games. Okay? But again, if you want to find the maximum of all of the losers to the max, okay, then you have 3 of these guys. And to find the maximum, you have to consider him to be the max, and then try him and him. Okay? So it's minus 1. You have to do 2 comparisons. You have to look at the depth of the tree and do 2 comparisons. Now, there is actually a way of programming this very interesting. You can find it on the internet. You just type in programming the tournament sort. It's a very nice thing. And n minus 1 plus log n is a lot smaller than 1.5n. So that's much, much better, and I think it is probably the best. Okay, I would like to go back before we finish section 9.1. There is one program that I would like to write. And do that. I don't want to waste your time doing it, so I'll write it. Okay, I just wanted to go through one of those algorithms that we talked about, was taking pairs of things and to find the maximum and the min, and to do it like that, to do it with pairs rather than doing each one. And I once gave it as a test question to write the algorithm, and people did miserably on it. So I thought it would be a good idea to actually write down the algorithm and go through it. It goes as follows, nothing to do with the cards. Here's the algorithm. You try the first 2, and you look, one is the max, one's going to be the min. So if A1 is less than A2, then min is equal to A1, max is equal to A2. Otherwise, if it's not, then min is equal to A2, max is equal to A1. So again, you try 2 cards, one of them is going to be min, one of them is going to be max. Then what do? This is a line you might not have seen. For I is equal to 3, 1, 2, 3. You start with 3 till n minus 1, and you're going to do it in step 2. In other words, instead of the usual, I plus plus, increment the counter 1, you do I is equal to I plus 2, because you're always going to take 2 at a time, 2 at a time, 2 at a time. Okay, so you do this follows. For I is equal to 3 to n minus 1, step 2. So 3, 5, 7, etc., etc. If AI is less than AI plus 1, you're going to compare. You're going to do a comparison. Okay, and if this is smaller than this, you're going to compare this smaller one with min. You're going to compare the larger one with max. That's what it says. Compare min to AI, compare max to AI plus 1. And if the comparison works, then you have to change and decide who's the new min, who's the new max. Else compare min to AI plus 1, compare max to AI. So that's a nice short little algorithm that works very, very well. Okay, just sometimes people have a hard time doing that. So I wanted to show you. Okay, fine. We're still doing the homework problems. Homework questions before chapter 9. Think of a way to find the median of an unordered array. About how many comparisons will have to be done. Okay, so the median. Let's just remember what the median is. I'm erasing the board. The median is the middleth guy. So if I give you a bunch of cards, or if I give you a bunch of cards, and I want the middle guy. In other words, if I was to sort them, who would be the middle? Let's just remember what we did in 3rd grade. The mean is the average, the median is the middleth guy, if we were to sort them, and the mode is the guy that shows up the most. Okay? We use the phrase bimodal curve or whatever. Okay, anyways. So, question. That is in no way sorted. Question, who's the median? Okay, who's the median? And by the way, we have 8 cards, so the median wouldn't be the middleth guy because there is no middleth guy. It would be the average of the 4th guy and the 5th guy. Okay, so who is it? What is it? Okay, answer. Well, or how do you find the median? Okay, so one very quick answer is as follows. Sort it and pop out the middle of the guy. That's a very simple thing. So sorting it is n log n. Sorting is n log n. Okay, we know 6 different ways of sorting things. Okay, but we can get them in n log n. Maybe you can get them in n, but that's a little bit cheating because as we saw, sorting in linear time is only for special types of inputs. But for general inputs, it's very hard to do it like that, but fine. Sorting is n log n, and then you go, if you have 100 elements, you pop out the 50th element and the 51st element, take the average of those 2 elements, and you get it. Okay, so that's how you find the median. Okay, question, can we do better? And the answer is yes, we can. So I'd like to show you a way of doing it. Okay, now obviously for these 8 elements it's not hard, but if you're given a lot of elements, if you're given 100 elements or so, what a big pain in the neck would be. Now again, you can solve it by just sorting it, but that seems not right. So here's something that we can do, something that we learned in chapter 7 when we talked about quicksort. Let's say you have 100 elements. Okay. Well, before I do this, I want to make the question a little bit harder. What's the median? The median is let's talk about from the bottom. The median is the 50th guy, or the n over 2th guy from the bottom. Okay? In other words, if you have n elements, the median is the n over 2th from the bottom. Let's say I ask you not what the n over 2th guy is from the bottom, but what's the ith guy from the bottom? What's the 10th guy from the bottom? What's the 20th guy from the bottom? What's the 500th guy from the bottom if you have 10,000 different numbers? What's the ith person from the bottom? So that's called the selection. It's called the selection problem. I think it's called the selection problem. You want to find the guy you want to select. Okay, you'll see what it's called. You'll read the book. You'll see what it's called. I'm sorry, I forgot. But we're going to solve that more general problem. Rather than only the n over 2th guy from the bottom, just any ith guy from the bottom. Okay, so you have 100 cards. You have 100 elements, and you want to find it. Well, one thing we saw we can do is we can split these 100 guys. Okay? We can split them as follows. What did we see about splitting things? Slowly splitting things. Chapter 7, when we were talking about the partition algorithm. Okay, so we're going to have a pivot element, and we're going to split them. Now I'm not going to talk about the pivot in particular. I'm going to put the pivot in one of the two categories. But let's say we partition these, and we get 38 in one of the partitions, and 62 of the elements in the other. Okay, and we split it such that these guys are less than these guys. Again, the 100 numbers are not in order. If the numbers are in order, you simply pop out the ith guy from the bottom and you have your answer. But if the numbers are not in order, we can split them like this. Okay, now let's go through this. Now you can do it again. Let's say I'm looking for I equals 50. I'm looking for the 50th guy from the bottom. I have 100 cards, I'm looking for the 50th guy from the bottom. Question. Where is the 50th guy from the bottom now? Okay, is he here or is he here? Well, let's think about it. If the 38th smallest element from the bottom are here, then the 50th smallest from all of them, take out those 38, is going to be in here. The median is going to be in here because the bottom 38 are over here. But he's not going to be the 50th from the bottom here anymore. What's he going to be? Here, I is going to equal, you're going to have 50 minus 38. I'm looking for the 50th to the bottom. I took out 38 of them, so minus 38 is equal to, what will it be in here? It'll be the 12th from the bottom here. Okay, great. Okay, just want to make things a little bit more clearer here. And it goes as follows. I'm going to have 3 numbers for each one of these. P is my starting number. P is the starting, in other words, you're given an array, okay, and here's P and here's R. So P is the first guy, R is the last guy. So that's 100. Okay? Okay. And you're looking for the 50th guy from the bottom here, but it's unordered. Okay? So then what you do is you chop them up like this and you say, look, here's the bottom 38 guys, here's the top 62 guys. Okay, great. Now, look what happens. P is now, I'm no longer looking at this. I told you, now that we know the 12th guy from the bottom, I'm going to chop this in 2. So now, P is 39. Here P is 1. Here R is 100. P is 39. Okay, great. And so P is 39. And what's R? Well, R is still 100. So you're looking in this part of the array, R is 100. Great. Okay, great. Now you're going to pivot. Okay, I'm sorry, now you're going to partition. What are you going to partition on? I have no idea. Could work out good, could work out no good. We saw whenever you partition, it depends on the data. Okay? But let's say the following thing happens. 37 guys here, you have 62 altogether, and 25 of them are here. Okay, and again, whenever you partition, all the elements on this side are less, all the elements on this side are more. Great. Question. Where is your 12th on the bottom here? Is he in here or is he here? Where is the 12th from the bottom? In here or in here? Now just remember, the 12th from the bottom in here is the 50th from the bottom in here. So that's exactly what we're looking for. Okay, so how do we do it? Okay, and the answer is the 12th from the bottom is in here. So I'm going to be chopping this up in order. But before that, I want to write up this is. Now, the 12th of the bottom in here, this is the bottom part. He has 25 elements. What's the bottom? Answer, 12. Still 12. Great. What's the P over here? Let me just show you what they have here. I'm not even going to write 38 over here because we're not even looking at that anymore. How did we split this up? We split this up into 25 guys here and 37 guys here. Now we're looking, P is still 39. I didn't move that, so this is P is 39 over here. And what's R? R was 100, but now what's R? R is 63. Is that true? Yes. Why? Because there's 38 here, and 25 is 38 plus 25 is 63. So let's just write down here, R is equal to 63. Okay? And again, just like over here, we're not interested in this part anymore. We're not interested in this part anymore. We're just going to chop this down, keep on chopping. Great. Let's say we do this again. And we have a bad pivot. We have a bad pivot. We have a bad pivot, and we split the 25 guys into 2 and 23. That's a bad pivot. And again, all these guys are less than these guys. Great. Where's my ith from the 12th? Where's my 12th from the bottom here? In here or in here? Answer: it's in here. Okay, let's just go through it. What's I going to be here? I is no longer 12 because I chopped out 2 of them, so it's going to be 12 minus 2, which is equal to 10. Okay, and now P is not going to be 39 anymore because we're going to move up 2, so P is equal to 41. And we don't change R. R is equal to 63. Okay, and we keep on doing this. Obviously here we're going to chop this out, etc., etc. Okay, let's just see what. By the way, here's the best thing that can happen now. Let's just do. We always talk about the worst case scenario. Here's the best case scenario. Ready? Here's 9. 9. 23 minus 9 is 14. Okay. And then, so here, I would equal to, I took out 9 of them, so I would be the 1th bottom. I'm looking for the minimal element there. And then if I did here, this would be 13, and this would be 1. Okay, 13 and 1, that would be, then this would be the one I'm looking for. Okay. Anyways, that's the best way, that's the best possible thing that can possibly happen, but obviously that doesn't happen. By the way, let's start from the top. What's the best way we can solve this problem? What's the best possible thing that can happen? Well, I'm looking for I have 100 guys here. I'm looking for the 50th from the bottom. So one way is I have 49 here and 51 here. I'd split this in 2. I could have it the other way and then we'd split. Okay, I'd split this in 2. I'd get 50 here and 1 here. Whoops. Nope. Oh, sorry. The other way around. Sorry. 1 here and 50 here. 50th from the bottom is right there. So in the best case scenario, I would do this in. Oh, how much work is done here? How much work is done here? Well, how much work does it take to do a partition? Answer: n. And here you're not partitioning all the elements, you're just doing n over 2 elements. So that's about 1.5 n. So this thing is about 1.5 n in the best case scenario. Okay, great. I'd like to write up the algorithm. The algorithm is on page, well, you don't have to waste your time. Okay, here's the algorithm. It's called Randomized Select. It's on page 216 of the book. It goes as follows. You give me an array. You give me the starting point of the array. You give me the ending point of the array. You give me the ith thing that you want. Which thing do you want? It's a recursive algorithm, so we have to do this. Okay. And first we have, since it's a recursive algorithm, we have to have the exiting condition, the base case. So if P is equal to R, in other words, P is the starting point. P is the starting point. Okay, here's P, and R is the ending point. Well, if P is equal to R, basically these 2 points are coming together. Well, if they came together, then return A of P. That's the guy that you want. Okay? Again, the starting point and finishing point, as you go on, get closer and closer. So when they meet, that's the point you want, A of P or A of R. Okay. Otherwise, here's what you do. Randomized partition, we saw this in chapter 7. Randomized partition means partition, but instead of pivoting along the last element, which you did, or which we did in chapter 7, randomly pick any of the element so that you'll get a better partition. Okay, and we'll talk about efficiency of the algorithm in 2 minutes, why this is a good thing, and then we'll even fix it much better. Okay, fine. So here's what it goes. Ready? Randomized partition. Use the partition algorithm to split them. Split what? You're given the beginning of the you go into the array. You're given the starting point. You finish the ending point, and you pick the pivot. Instead of me picking the pivot as the last element, you randomly pick the pivot. Great. Q minus P plus 1 is what? Okay. This is the size of the right, oops, sorry, left. Okay, not the midpoint, but the Q, take away the P minus 1, this is the size of the left part of the partition. Okay, remember, randomized partition splits it, chops it in two, and gives you the chopping point. Where is it chopped? Right over there. So Q, take away the starting point, that's the size of the left part. And now we have to determine, do we look in the left side, do we look in the right side? Now we did this for all the cases, but let's just do this. If I, that's the one you're looking for, is less than the size of the left part, that means it's in this part. Okay? So then return randomized select, do the same thing. Okay? Do the same thing, it's a recursive algorithm, but now look what you do. The array A from the beginning part till before the partition. Here's the pivot thing. Okay, I drew the picture a little bit wrong. The algorithm is the right thing because I wasn't concerned. The truth is I should have drawn the picture like this. Here's 100 elements. Here's 37 elements. Here's 1 element. And what's that? 38. So that would be 62 elements. Okay? This is the right way I should have drawn the book. Okay? This is the right way I should have drawn the algorithm. Now let's just do this. Return. Now, if I, the one you're looking for, is smaller than K, that means it's in this side. Okay? And then select the algorithm like that. I'm sorry. Randomized select, recall itself from A to Q minus 1, that's this part, do the ith part. If I is in here, then look over there. Else, what's the else? Else it's not in here, it's in here, it's in this part. Okay? And so return randomized select, A, Q plus 1, R minus 1. Let's just go through this. A is the array, Q plus 1, that means here's the partition point, here's where the pivot is. Go past that, past the Q. Here's the Qth point. Here's Q plus 1, that's from here, till R, till the end. And what do you look? You look for the I minus K element, because you have K elements over there. Move it away. I minus K elements, so that's over there. Okay, so this is the algorithm. Question, how much work is done? Well, it all depends on how your partition algorithm works. What's the worst thing that can possibly happen? Okay, let's go through it. The worst thing that can possibly happen. Well, the worst thing that can possibly happen is as follows. You have 100 elements. I'm just giving you, I mean, obviously I should talk about n, but let's just talk about it. You have 100 elements. You partition them into 99 and 1. That's a pretty stupid partition. That didn't save you a lot. 99 and 1. Okay? Then you partition, obviously, let's say you're looking for the 50th one in the bottom. It's going to be in here. Let's say you do it again, and again, the gods are against you, and you don't have a good partition. And there's going to be 1 over here, and 98. There's a song that goes with this. 98 elements to partition. If one of the partitions should happen to go, 97 elements to go. So if one of them happens to go, you have 96, etc., etc. Okay, question, ... So if you have that's a really bad partition. When there's only one guy there, that's a really bad partition. Now, let's assume, well, question, how much work is done? For each one of these partitions, how much work is done for a partition? N. So I'm going to do N operations here. Here's really I'm doing N minus 1 operations. That's fine. How many operations am I doing here? N minus 2. 100 minus, I'm doing 100 partition, I'm doing 100 operations, 99 operations, 98 operations, etc., etc. Okay? So add up N plus N minus 1 plus N minus 2 plus N minus 3 all the way down. I get, think of Mr. Gauss's trick, N squared operations. Okay, N squared operations. This is a really stupid thing to do. Why? Why is it a stupid thing to do? Because I told you, if you want to find the ith thing from the bottom, sort the list and pop out the ith element. You don't have to do all this hard work. Just sort it and pop out the ith element. That's n log n. N log n is a lot better than n squared. So this is not good in the worst case scenario. However, the book does a whole analysis. You're not responsible for the whole analysis, but the book does a whole analysis to show you that on average, okay, it's n on average, the algorithm was n. It does n operations. And the reason is as follows. Just think about it. Okay? You have n elements. Let's say you skip n over 2 over here, n over 2 over here. Great. That takes you, and you keep on doing it. You're going to have n over 4 over here. You're going to have n over 8 over here. Okay? So how many layers are you going to go down? And the answer, I'm not going through the entire thing. How many layers are you going to go down? Answer, this is going to be log n height. Great. But notice here, you're doing, in order to get this partition, you're doing n operations. Here, you're doing n over 2 operations. Here, you're doing n over 8 operations, etc., etc. They're getting smaller and smaller. And so it's not log of n times n operations. Each time it gets smaller and smaller. And the book goes through analysis and shows that on average, it's n operations. The entire thing. N operations is better than n log n. So on average, it works better than sorting it, which is very interesting. Okay. But then the book does something very, very interesting. And this is section 9.3. Section 9.3 fixes this algorithm. Section 9.3 fixes this algorithm so that it works, worst case, n. Okay, so let's just review what we just did. You reviewed it, what we just did. We just said worst case is n squared. Average case is n. Okay, and the book goes through a whole analysis and says that the average case probably, even in bad cases, it's still linear. Okay, but then they fix it. Okay, and they fix it so that in the worst case, it's n. And that's a really beautiful algorithm. The only thing is, it's a little bit hard to understand. So thankfully, I wrote up a little page to show you how it works, and it's totally, totally understandable. Okay, and the point here is, okay, so it's in your booklet. We're going to go through it very carefully, but I just want to show you how it works. Okay, we'll just erase this for a second. Okay. A lot of this you're going to have to read in the book. It's very readable once you understand what the hell they're doing. Okay, and it's very understandable what they're doing because what are you fearful of? You're fearful of having a bad pivot. Great. So what I'm going to show you is how you not have a bad pivot. Okay, so here's a page from your thing. We're going to go through it together. Okay, here's how you do, it's called the selection algorithm. You select the ith element. Okay, so take a bunch of elements, 32 elements. Here you have 32 elements. I don't know how well you're going to be able to see this, but you have it on your paper. That's very good. Your 32 elements. Just try looking at those 32 elements and trying to see who's the median element. You have no idea who the median is. Okay, great. That's fine. Okay. Okay, so there's a few step procedure here. First step, separate them into groups of 5. 5 is important. So I put them in an array, each one of 5. I made up this sheet. Great. Next, for each one of them, for each group of 5, find the median element. Okay? And so here we put the median element. Okay, 23, 14, 30, 53, 62, 89, that's the median element. Now finding the median of 5 elements is not a hard thing. You could do it in 3 operations. You just want to 3 or 4 operations. Okay? Okay, great. Okay, notice here, you're going to find the median elements. Notice here, you're going to find the median element, and you're going to put the median element in between. Notice these are not sorted. 23, 14, 53, 62, 89. Okay? The only thing I could say is here's 50, here's the median element. The guys less than it are above. The guys more than it are below. Okay, hey, same thing here. 63. This is the bottom part is not sorted, doesn't bother us. The guys less than it are above, etc., etc. Okay, so you have n elements. You've chopped them up into n over 5 groups. Okay, and each group you have that median. Now, take your n over 5 elements and now find the median of the medians. That's this guy. In other words, go through, take all these bold-faced guys, those are the medians, and find the medians of the medians. Now, hold on a second. How do you find the medians? Oh, it's a recursive algorithm. How do you find the median? The whole purpose is to find the median element, let's say. How do you find the median of the medians of this group of n over 5 medians? It's a recursive algorithm. Okay, great. Okay, now this median of the median is 53. Let's just go through this. 34, 28, that's less than 53. 63, 61, that's more than 63. So you take these columns and you rearrange them so that you have the median and the medians over there. Great. Okay, now, what can I say about these elements? Okay, I'm going to use, doesn't come out very well here. Sorry about that, but I'm going to do it here. Okay, let's look at this. Here's 53. Okay, all these medians are less than 53. Great. All the guys above the medians, that's here, are less than 53, right? Because, let's go through it. 53, here's the median of the median, 53. Everything this side is less than 53. Everything above the medians are less than that. So these guys are, all of those guys are less than 53. Great. Let's go to the other side. Hold on. Got to change pens. Hold on. Okay. Now, here's 53. What can we say about all these guys? What can we say about all the people that way of 53? Well, they're all more than 53. Great. Okay. And what about those people above, below those? Well, not only are they more, but so are these more. Okay, so all these guys in red are more than 53. Okay, this one is also more than 53. Okay, sorry, this one's also more than 53. So all these guys are less than 53, all these guys are more than 53. Great, so now what are we trying? What's our aim here? Our aim is to get a good pivot, okay? Because once we have a good pivot, we're going to be good, okay? Life will be great, okay? So here's what we do. You have your end cards. You have your n cards. Now, what you do is you find the pivot. You find the median of the median, which turns out to be, which you'll use as your pivot. Now, why will you do that? Okay, so I'm going to split it like this, and here I'm going to say m of m. That's the median of the median, right over there. Okay, now some things are going to be there, and some things are going to be there. Okay, now if you look, what I just did was I chopped this box pretty much into 4. 1/4 of them, so n over 4 of them, are less than it, less than the median of the median. 1/4 of it is more than the median of the median. That's very good. Okay, great. What about the rest? What about these things? Well, let's go through them. Okay, I'm assuming you have this now. Here's your 53. Here's 45, that's less than 53. Here's 85, that's more. Here's 62, that's more. Some of them are more, some of them are less. Okay, let's just go through this. Here's 53. All these guys are less than 53. All these guys could be more. Okay, all these guys are more than 53, but all these guys, some of them are less than 53, like 43 and 23. And some of them, like 77, are more than 53, so you can't really tell. Okay, so great. So if I choose the median of my median as my pivot, then 1/4 of them will be here, and 1/4 of them will be here. Great. What about the other 2/4? Well, I'm going to have to check each one individually. Some I'll put in here, some I'll put in here. Okay, now, if there's justice in the world, about half of those guys will go into here, half of those guys will go into here, and I'll have a 50-50 split. That would be great. Okay, but there is sometimes no justice, and we're always looking for the worst case scenario when there is no justice. So what's the worst possible thing that can possibly happen after I split up with the median and the median? Well, the worst possible thing, and I'm being slightly inexact, the book is being much more exact. The worst possible thing is, let's say, 3 of these. So I check each one of these other things that are white. They're not green and they're not red, they're white, and all of them land in here. So that's these white guys and these white guys land in here. And this is alone. Now, what can be the worst case scenario here? Do I have to further chop off here or chop off here? What's the worst possible thing that can happen? Do I do more partitions on this side or this side? Okay, well, the worst case scenario would be I do partitions on this side. Okay? And again, you have to chop. So, let's just go through. The worst case scenario is, and the book has this whole long analysis of it, but I'd like to show you it. The worst case scenario is I have n guys, okay? I do a lot of work to get the median of the median, and we saw how much work is done, okay? And then, so a lot of work. I'm just going to write a lot, okay? The book goes through exactly. But then I have to do T, then I have to chop it again this side, because this would be the worst side. By the way, I would love it to be this side, right? We want small elements, but bad things happen. Murphy's Law, it's probably going to be there. So this would be n plus n plus n. This would be 3 over 4n, plus a lot of work. Okay. Anyways, the book does through a lot of analysis. It's very pretty, it's very nice, but it turns out that this whole thing is O of n. O of n. It's linear. It's linear. Now, there's a lot of work there. O of n means there's a leading coefficient there. There's a lot of work there. I think the coefficient is something like 17 times n. Something like that. Now, 17 times n, it might be better to do n log n. Just sort the damn thing and pop out what you want. So there's a lot of work there. This is more theoretical work. Think of it. You can explain it to a 6th grader. I give you a list. I want to know how to find the ith from the bottom element. How do you do that? How do you find them? I think very few people will come up with a linear algorithm to do it. This is a linear algorithm, but the shocking thing is, in the worst case scenario, it's still a linear algorithm. Okay, and it's 17n. So you're going to have to determine when to use log of n, n log n. You want to know when, for what values of n is 17n less than n log n. Okay, and you can figure it out. Divide both sides by n, you get 17 is less than log of n. Okay, so it has to be pretty big in order to use it this way, but it's just an interesting algorithm that they were able to do it. And it's worked out very, very nicely. In the book it says 7n over 10. Instead of 3n over 4, it's 7, instead of 3n over 4, it's 7 over 10. They're a little bit more exact than I was. I was just trying to show you the intuition of how it works. But obviously they're correct and I am wrong. Okay, so that's the end of chapter 9. Okay, let's just go through a few things. Chapter 10, so we are now finished the sorting and the numbering things, and we now move on to do different things. Chapter 10 is a review of all data structures, okay? Queues, linked lists, and all that. I strongly recommend that you read through that chapter. It's very, very readable, and it gets the notation that you're going to use the rest of the semester. So it's very important to do it. I assume you all saw it because it's a prerequisite for this class, so you know that stuff. Queues, stacks, linked lists, doubly linked lists, etc., etc. That's chapter 10. Chapter 11 is hash tables. Very important, used all over in business. You might have even seen some of it. Very readable. We're not going to do it simply because of time considerations, but not because it's not important. Okay, and we're going to start next week. We're going to start binary search trees, which is chapter 12. Okay, anyways, I hope you enjoy. I hope you're doing the problems, and take care.